Well, hi there. This is Dr. Dell, and this is the interlude on complex numbers and trig that you've come to now, the fifth interlude in the teaching math book that you are presumably reading to get to these interludes. I'm Craig Hain, of course. My students call me Dr. Dell, and you can learn a lot more about all of this at triadmathinc.com. And I want to talk to you today about something that we cover in Tier 4. Now, as you know from reading this book, there are actually 10 tiers in the math curriculum that I'm proposing for high schools. The first six tiers would be the ones that almost all students would go through to prepare for a science, technology, engineering, or math career in university, so-called STEM career. And the last four tiers are only for those rare, precocious students that might actually want to perhaps become mathematicians. However, this would be covered in Tier 4. And in Tier 4, as you know, we go through the Dr. Simmons book for the second time and make sure that we cover all of the proofs that we didn't do in Tier 3 in it, so it's completely done. And in fact, when a student gets done with Tier 4, they will have a tremendous preparation for calculus, which then we cover in Tier 5. But one of the things we cover in Tier 4 is complex numbers. And I want to show you something that I do that helps me in complex numbers remember some trig identities. Trig identities, of course, we've learned by then are very important. And one of the trig identities that we want to know is cosine of alpha plus beta. What does that equal? And another one is sine of alpha plus beta. Now, in Tier 4, we have discussed complex numbers. I'm going to assume that you understand the complex number system, that you're a teacher and that you understand it. This is not for beginning students, this discussion. As you know, of course, the complex number system are the numbers that correspond to points in the plane. So I'm going to review this very quickly. This is not really the way I would teach it to a beginner. We go much more slowly and elaborately in the training in Tier 4, but I don't have a notebook to show you on it right now. So basically, you have the real number line, and it corresponds then to the real numbers. And we've learned all about that, of course, back in the foundation course. And then you take a vertical line that is another real number line, and you label it with the same numbers, only where these were called real numbers, you call these imaginary numbers. So this would be I, and 2I, and 3I, and so on. Now, those are names that are unfortunate. They're historical names. This is called the real axis. This is called the imaginary axis. Well, this is just as real as that. This could be the red axis and the blue axis. It'd be fine. And then, if you take any number in the plane, if you drop down here and that is A, and if you drop over here and that is BI, then this number is called A plus BI, which is what it would be if you used the addition of vectors to get. And it's called a complex number. And one of the things that we learn then in complex numbers very early on is there's two ways. Well, first of all, addition is very easy. It's just vector addition. But there's two ways to define multiplication. And one is the algebraic way, where you would just take two complex numbers and multiply them out and use the fact that I squared is equal to minus 1. And then the other way is geometric. So there's the algebraic way and there's the geometric way. And the geometric way, of course, as you know, if you know complex numbers, is if you take two complex numbers here and here, and if this is alpha, I'll say theta, and this is beta, then the sum, or the multiplication of them, is you take the number which is theta plus beta, and that's and then you take this length times this length. This is L1, this is L2, this will be L1 times L2, and that will be the product. But the big thing is you've added the two angles. And I went over that very fast. If you know complex numbers, you followed it. If you don't, you need to study complex numbers. The best resource I know, I hate to be biased, is Tier 4. Because we present it in a very logical, methodical way. Now, having said that, and in fact, I tell you, I consider the most important equation in all of mathematics myself to be This geometric definition of complex numbers is equivalent to the algebraic definition, because from that so much flows. And we start out with trigonometry. We know that if we take x as a complex number, cosine a plus I sine of a, y is cosine b plus I sine of b. Those are two complex numbers. We multiply them. We can use the algebraic definition and multiply them out. Or we can just add the angles, and the product is cosine of alpha plus beta plus I sine of alpha plus beta. And then that equals these two multiplied our standard way. Now what that means is that the cosine of alpha plus beta is going to be the real part of this when you multiply it out, and that'll be cosine alpha times cosine beta. And then when you take I sine alpha times I sine beta, that is I squared sine alpha sine beta. I squared is -1. That's where the minus comes from. And so you get sine alpha sine beta. And this is the real part of this product, this algebraic product. The imaginary part, sine alpha plus beta, then is what? Cosine alpha times sine beta plus sine alpha times cosine beta. That's the imaginary part. So here are the two identities. And the way I remember them is this very thing here. Now, this doesn't prove them. As a matter of fact, the way you prove these two definitions are equivalent is you have to know this in advance. You have to prove this another way, and which we do, by the way, in the Simmons book. In George Simmons' book, we prove these. However, the Simmons book does not discuss complex numbers at all. But of course, it gets us ready for it. So then we're able to very easily prove the equivalent of these. Once you know that, then you can work backwards as a mnemonic device to get these identities and a whole lot of other identities. In fact, I remember almost all of the trig identities by how I derive them from what I know about complex numbers. I have a very bad memory, and it's hard for me to remember formulas. And in fact, throughout the foundation course, I emphasize to the students that you should always try to derive the formula quickly from something you understand, whether it's the area of a triangle or the surface area of a sphere or whatever it might be. And we emphasize that. Of course, in the case of the spheres, you know from the previous interlude, that's not easy to do unless you have some pretty good mnemonic devices. But this is what I use for deriving all kinds of trig identities. I use the fact that what I know about complex numbers. And then in the last interlude, I'm going to talk about complex numbers again and show you one last thing that we cover in Tier 4 that really is kind of the ultimate test. Did you really understand complex numbers? So this is Dr. Dell signing off, and I will talk to you on the last interlude. Bye-bye.